Now, in the multi-level queue, we have different queues, and in all the queue have different processes that can come. So system processes will go to the system queue, interactive process will go to the interactive queue, and batch process will go to the batch queue. And based on the scheduling algorithm on that particular queue that will apply, will provide the CPU to that particular process. Now you see the system process, because it has the highest priority, so it will get the CPU first, right? Definitely, and will give the CPU to the system process because it has the higher priority, and then we'll provide the interactive process the CPU, which is a medium priority, and the batch processes will get the CPU at very last. So in that way, we divide the different queues here, and we'll try to find it out different types of queue, and then we'll execute the process. Now, what was the problem with the previous type of algorithm? So in the previous type of algorithm, we'll put all the process together. So whether it is a system process, whether it is an interactive process, whether it is a batch process, all the process will put together in one queue, and we'll put any of the scheduling algorithm to execute this. So this is not the right way to treat different type of processes in at once, right? So we'll not put all the processes into one platform. So that's why a multi-level queue type of architecture has come into the operating system, and the higher priority will the one queue was there for the higher priority, for medium priority, and for the lower priority processes. And we may apply different scheduling algorithm in different queues. So it is not like round robin will be used only in the system processes. It may be shortest jobs first, it may be shortest remaining time first. So whatever the algorithm that is there, we can apply there. Okay. Now, what will happen after that? In this particular system, there is a problem. Now, what is the problem? The problem is, if let's say all the time we are getting the higher priority process, so the lower priority process will not get the chance to get into the CPU, right? So, but it will not happen here because all the processes are in the same platform, and we want to, if we want to have the batch process, the number of batch process came, then we use the batch process and put into the CPU. When the scheduling algorithm will choose any interactive process, we'll take the interactive process. So there is no differences between all those processes. It is taken in a one platform. But here we have some problems, like system processes will be executing into the CPU because it has the higher priority. And you see, if most of the time we are getting the system processes, so the interactive process or the batch processes will not get the chance to execute into the CPU. So for this multi-level queue, even though it is differentiating between all the different processes, but there is a drawback of starvation. So starvation means these lower priority processes may never get chance to execute into the CPU, which is not a good practice in operating system, because the operating system is just like a manager which will manage whole resources into the operating system, and it has the responsibility uh, to be fair for all the processes that are requesting for any resources. So the multi-level queue has a drawback, and to see that particular drawback, another architecture comes into the picture, which is called multi-level feedback queue. Now it is also multi-level, but here we have taken some feedback, and this feedback we used to take so that the lower priority process will get the chance to execute into the CPU. Let's see how it will take place. So let's assume that we have the queue. Definitely we have multiple queues here. So we have, let's say, the multiple queues. Like the previous example, we have multi-level queues. And all these queues will be leveled based on the priority itself. But the first queue will take as a lower priority or lowest, or yeah, lower priority you can write. Lower priority process will be taken into the first queue, and the highest priority process will be taken into the last queue. Okay, so we get the input as a highest priority and we'll get the input as a lowest priority in the first queue. Now here, the time quantum that has been taken as let's say the time quantum here, let's assume that it is 2. So here we'll take the lower priority process, which is a batch process, right? And there is some medium priority process that will take up. But here we'll take the lowest priority process, and here maybe we'll take some medium priority processes. Now what will happen is, let's assume that we got one batch process, process 1, which is a batch process having burst time as, let's say, 10 or let's say 12. Okay, so what will happen here? Because the first queue is there, so definitely the first queue is going to execute itself. Now the first queue will be executing here and given the CPU for how much time, the time quantum is given. So here it will act as a first come first serve, but the time quantum is there, means it will work as a round robin algorithm, and the CPU will be allocated to that. Once the time quantum will be finished, the process P1 will be given chance to be in, if its burst time is also once left or remain, then we'll put into the second level. So we have second level queue, which has time quantum is higher than the first one, and it will execute in this again in the first come first serve basis. So whoever process is coming first will get the chance into the CPU. And once the execution is finished for the time quantum, if the burst time is left, then we'll put into the third one. So definitely how much will be left? Previously 2 has done, so 10 is left. In the second queue 4 is done, so 6 is left. And we'll put here, and here the time quantum is 8. In that way, it will execute here. The time quantum is 8. It required only 6. It will execute all its burst time and it will be terminated. If it is not terminated and still there is some, you assume that still there is some burst time left. So it will go to the highest priority queue and will get the chance here again. So it is a first come first serve without any time quantum. So it is not a round robin. All those are round robin, but this one is the first come first serve. So whatever is left will be executing into the CPU. Now here what we are doing is the higher priority process is getting the CPU, as well as the lower priority process is also getting the CPU and increasing its priority. So you can see here the lowest priority queue will put here, and it is slowly going to the highest priority process. Highest priority queue. So it is entering into the lowest priority queue, and slowly, because of the feedback, it is moving towards the highest priority queue. So here the starvation problem will be removed, because whatever your higher process is available, the lower process will get the chance to interact with the CPU. Means the response time is lesser than the previous model, which is a multi-level queue model. So starvation problem has been removed. So there is no starvation problem here. Okay. And here we can apply round robin, or you can apply, let's say in some, you can apply shortage of, so it is depend upon which type of architecture is giving you optimum result. So based on that, you can do it in a standard way or in the different books. The level is here, I have put it 4 level of queue. In some book, it is 3 level of queue. So it depend upon book to book, and it depend upon operating system to operating system, which type of multi-level feedback queue they have applied. But you see, the multi-level feedback queue is very much essential for the interactive operating system, or the operating system which we are uh, thinking that has the highest throughput. So in the multi programming operating system or multitasking operating system, we have to look forward about these type of scheduling algorithm, which is multi-level feedback queue type of scheduling algorithm. Okay, so the starvation problem will be removed from here.